I'm very happy to be here today. And I will try to convince you how integrative single-cell multi-omics analysis are powerful to understand leukemia resistance. So, as you should know, the leukemic population is highly heterogeneous. And thanks to single-cell technologies, we start now to understand the basis and the consequences of this heterogeneity. In the lab, we are interested in acute lymphocytic leukemia, the M3 subtype of acute myeloid leukemia, AML, which is driven by the expression of the oncogenic fusion protein, X-RARA. So X-RARA involves the RARA receptor, which is fused to different partners, such as PLZF or PML. And the expression of X-RARA protein induces a blockage of differentiation at the promyelocytic stage. And one clinical particularity is that most of APL patients can be cured by differentiating agents such as retinoic acid. However, APL patients bearing PLZF-RARA are resistant toward retinoic acid, which fails to eradicate the leukemia eliciting cells. Thus, PLZF-RARA patients exhibit poor prognosis. And experimentally, how leukemia relapse is working. So we grafted PLZF-RARA leukemic bone marrow into recipient mice. We treated these mice with retinoic acid. And what we could observe, it is PLZF-RARA degradation and cell differentiation, full differentiation of the leukemic cells. However, if we transplant again the leukemic bone marrow treated with retinoic acid, so here we stop the retinoic acid treatment, we can observe relapse associated with PLZF-RARA expression. So our objective was to identify and characterize the relapsing stem cells, and to do that, we perform leukemic bone marrow transplantation, treated mice with retinoic acid, and we perform single-cell transcriptomic and epigenomic analysis. So at first, we analyzed our single-cell RNA-seq dataset. We integrated both datasets, untreated and retinoic acid treated cells. And what we can see, it is transcriptional dynamic upon retinoic acid treatment with the appearance and the disappearance of the specific cells. And when you have a single cell data set, after that, you can do a clustering. Like this, we identify 6 clusters, and we look at biological processes associated with each cluster. So we found 3 clusters from 1, 2, and 3 exhibiting neutrophil signature, which correspond to the stage of differentiation of leukemia, I mean promyelocytic stage. We also found 2 clusters, NOERA1 and NOERA2, which strongly express myeloid transcription factor and located at the end of the trajectory of differentiation. So this is the cluster of cells sensitive to retinoic acid. And we found another cluster with TNL repair, replication, and proliferation signature. After that, we look at the cell distribution in each cluster. And what we observe is that the red cluster was composed as many of untreated as retinoic acid treated cell, suggesting that this cluster does not seem to respond to retinoic acid. So after that, we wanted to further characterize the unresponsiveness of the retinoic acid, the red cells. And we took advantage of different signature obtained in a UDT paper. So the first signature reflects the retinoic acid sensitivity. And what we found is that this signature is highly expressed in the NOERA cluster. And the second signature is an E2F signature, and this signature reflects the retinoic acid resistance, and we confirm that this signature is highly expressed in the RAP cluster. So after that, we attempted to purify the red cells, taking into account the expression of surface marker that we found identified in our single-cell RNA-seq dataset. But we were limited to isolate the red cells from the PROM cells, so we purified the pro-red cells and the NERA cells. And we look at PLZF-RARA expression, and we found that upon retinoic acid treatment, PLZF-RARA was never detected in the bulk population nor in the NERA cells. However, the pro-red cells still maintain PLZF-RARA expression and keep also the potential to develop leukemia in mice. And what is also interesting, we took advantage of Affymetrix data obtained in patients, in PLZF-RARA patients, and in PML-RARA patients, so PML-RARA, which is sensitive to retinoic acid treatment. And we found that the pro-rep signature was positively correlated with PLZF-RARA patient, while the NERA cluster, the gene signature, was associated with PML-RARA patient. So here we can conclude, we can hypothesize that the RAP cluster seems to be a driver of retinoic acid resistance. And after that, we wanted to further decipher the regulatory networks involved in this process. So we perform a single-cell epigenomic analysis. We perform a single-cell attack-seq, which is a technique which allows to monitor the chromatin opening. And we integrated RNA-seq dataset and attack-seq dataset, and we transfer the cluster information from our RNA-seq dataset to the attack-seq dataset. And interestingly, what we found is that the red cluster here in yellow was not impacted in terms of attack peak number upon retinoic acid treatment. And it is also true at the signal level. We have a very few change upon retinoic acid treatment. And moreover, the red cells differ from the other cells in their chromatin states. They exhibit more close ties. And this data suggests that besides transcriptional reprogramming, epigenetic alteration may also predispose the red cells to not respond towards retinoic acid. So after that, we decided to focus on regulatory networks. So as I told you, attack able to monitor the chromatin opening, and when the chromatin is open, it becomes accessible to transcription factor, and we can identify transcription factor motif, which are a specific sequence recognized by the transcription factor. And the integration of both datasets allow to look at regulon activity. Regulon activity is a transcription factor, and it's binding to target gene, and it takes into account the expression of the transcription factor and the expression of the target genes. And we apply different filtering, and we, like this, we identify 3 main transcription factors from the E2F family. And we look at the target genes shared by these 3 transcription factors, and these target genes are probably drivers of retinoic acid resistance. And among these target genes, we identify EZH2, which is deregulated in many cancers, and we found that EZH2 was highly expressed in the red cells, and its expression is also increased upon retinoic acid treatment. So what is EZH2? EZH2 is the methyl transferase of PRC2, polycomb repressive complex 2. And what is interesting is that EZH2 can harbor different activity. So its canonical activity consists in the trimethylation of H3K27, and this induces the repression of gene transcription. But EZH2 can also harbor non-canonical activity. It can methylate non-histone substrate, but EZH2 can also have non-methyltransferase activity. And in this line, we previously reported that EZH2 can behave as a transcriptional activator and can associate with active histone marks such as H3K4 trimethylation. So to validate the relevance of EZH2 in our model, what we use, it is a conditional knockout model for EZH2. We purify lineage negative cells from these mice, and we transduce the cells with a PLZF-RARA, and we induce in vitro EZH2 deletion, and we perform repeating assay. And what we found is that upon EZH2 deletion, we can observe a PLZF-RARA degradation. Cells, the leukemic cells, are not able to replate anymore. And EZH2 deletion induce also cell differentiation. So altogether, this data suggests that EZH2 loss leads to PLZF-RARA degradation and leukemia clearance. And we use another model, the PLZF-RARA leukemic bone marrow, and we transduce this leukemic bone marrow with an SH EZH2. We knock down EZH2, and what we found, it is upon the down regulation of EZH2 expression, this increase the mice survival and delay the leukemia development. So after that, we wanted to know which activity of EZH2 is important for this process. So at first, we look at the canonical activity of EZH2. And as readout, we monitor H3K27 trimethylation, both at the global and chromatin level. And what we found is that upon retinoic acid treatment, we observe a decrease in H3K27 trimethylation, both at the global and the chromatin level. However, what is interesting here is that we observe an increase in EZH2 expression, as we show in our single cell NSEC. And this data show that there is a discrepancy between EZH2 protein level and its methyltransferase activity. So maybe we thought that the residual activity of EZH2 was important for the process, so we decided to target this residual methyltransferase activity by using the GSK, which inhibits the catalytic activity of EZH2 that we combine with retinoic acid. Unfortunately, this treatment did not clear leukemia, and we observed a relapse. So finally, we look at the non-methyltransferase activity of EZH2, at the non-canonical activity of EZH2, and we use an EZH2 degrader. And we treated our leukemic bone marrow with EZH2 degrader. And what we found is that we observe leukemic cell differentiation, and we observe also PLZF-RARA degradation. And the EZH2 degrader kills leukemic cells in vitro, and when combined with a retinoic acid treatment, significantly prolongs mice survival. Finally, we wanted to know if this EZH2 degrader would target the red cells. So the red cells exhibit DNA repair, DNA replication, and proliferation signature. And what we found is that treating cells, the leukemic cells with EZH2 degrader, target biological processes such as DNA replication and proliferation, while the GSK has no impact on these genes. And we confirm that EZH2 degradation profoundly affects the REP genes, while GSK has a very little effect on the REP genes. So, to conclude, so thanks to single-cell technologies, we identify cells resistant toward the racemic acid, exhibiting DNA replication, proliferation signature. We showed that EZH2 was involved in this process, and we showed that targeting pan-EZH2 activity was necessary to clear leukemia. And here, just to go beyond the real context and racemic acid resistance, so in collaboration with Jean-Emmanuel, so we reanalyze single-cell RNA-seq dataset. So it was an AML patient in a PDX model treated with ven Araci and ven plus Araci. And what we did, we integrated both datasets and we performed a new clustering. So naively, I was looking for the cells resistance to the chemotherapy. So I took advantage of the high OXPHOS signature. So we found here two cluster of cells exhibiting a high expression level of this signature. And interestingly, these cells harbor also a REP signature and highly express EZH2. And Emin calculated an EZH2 signature by using BetaML and TGCA platform. And what we found is that this EZH2 signature was highly correlated with a low responder. And what is also interesting is that the non-methyl activity of EZH2, as well as the REP signature, seems to be associated with AML relapse. So this data suggests that the signature of the non-canonical activity of EZH2, as well as the REP signature, can potentially be adopted for AML patients and chemotherapy resistance. So I would like to thank all the members of my team in Marseille, in Estelle Dupré laboratory, more especially Nadine Platet, who set up all the mouse model, and Adrien Masuel, who performed all the single-cell analysis. I would like also to thank our collaborator, more especially Atsushi Iwama, and all the platform of the CRCM and all the sponsors. And thank you for your attention, and it will be my pleasure to answer your questions.